Welcome to this quiet corner of the world, a gentle space for stories designed to soothe your mind and guide you toward restful sleep. Tonight, we begin a long and peaceful journey into the heart of scientific discovery, not through the lens of methodical planning or brilliant deduction, but through the soft, strange, and beautiful light of serendipity. We will explore 50 facts about the happy accidents, the fortunate stumbles, and the unexpected gifts of chance that have illuminated our understanding of the universe. Before we begin our story, I would love to know where you are listening from tonight, or perhaps a simple reflection on your day. Your presence here is deeply appreciated. If these stories bring you comfort, please consider supporting this channel with a like and by subscribing. Thank you so much. Now, find a comfortable position. Let your body feel heavy and supported. Let the day dissolve and allow your mind to drift with my voice as we begin our tale. It often begins in silence, in a place of neglect. Imagine a laboratory in London in the late summer of 1928. The air is still and filled with the faint, musty scent of dust motes dancing in the slanted afternoon light that filters through a tall, grimy window. On a bench, amidst a clutter of glass vials and burners, sits a shallow glass dish, a petri dish, forgotten. It was left here by a bacteriologist named Alexander Fleming, who had departed for a 2-week holiday, leaving this small, sealed world to its own devices. This is where our story starts, not with a bang, but with the quiet, inexorable bloom of a common mold, a tiny spore of penicillium that had, by some unknown breeze or open window, drifted in and settled upon a culture of Staphylococcus bacteria. Upon his return, Fleming, a notoriously untidy scientist, began the mundane task of cleaning up his workspace, sorting through the dozens of dishes he had been cultivating. One by one, he dipped them in Lysol to sterilize them for reuse, but his eyes, trained by years of looking, paused on this one particular dish. He could have so easily dismissed it. It was a failure, a contaminated experiment, a piece of scientific refuse to be washed away without a second thought. And perhaps 1,000 other scientists, in 1,000 other labs, had done just that. But Fleming noticed something peculiar. All over the dish, the bacteria had grown into milky, opaque colonies, a thriving, microscopic city. But in one area, around the fuzzy, blue-green island of mold, there was a perfect, clear circle, a halo, a moat of death where the bacteria could not encroach. It was as if the mold was whispering a secret, a chemical command to keep the invaders at bay. And in that moment of quiet observation, Fleming was the first human being in history to truly listen. This, he would later realize, was a visible manifestation of a phenomenon called antibiosis, the silent, ancient warfare that has been raging between microorganisms since the dawn of life. In the unseen world beneath our feet, in every handful of soil and every drop of pond water, fungi and bacteria are locked in a constant, sophisticated battle for resources. They produce an arsenal of chemical weapons, toxins, and inhibitors to carve out their own territory. The penicillium mold was not creating a medicine. It was simply defending its home, producing a substance that could rupture the cell walls of its bacterial competitors. What Fleming had stumbled upon was not an invention, but a conversation that had been happening for 1 billion years. He had simply, through a happy accident of contamination and a lifetime of curiosity, learned to understand its language. This moment of serendipity was not a singular flash of lightning from a clear sky. It was more like the slow gathering of clouds that had been forming throughout Fleming's entire career. Years earlier, in 1922, he had made another accidental discovery. While suffering from a cold, a single drop of his own nasal mucus had dripped from his nose into another petri dish teeming with bacteria. He forgot about that one too for a time, but when he returned to it, he found that where the mucus had landed, the bacteria had been dissolved, as if washed away by an invisible tide. He had found lysozyme, a natural enzyme present in our tears, saliva, and mucus that acts as our body's own first line of antibacterial defense. That discovery, while not as world-changing as penicillin, had tuned his mind to a certain frequency. It had prepared him to see the profound significance of an empty space in a sea of life. This is the very heart of what makes serendipity so much more than simple luck. It is the beautiful and mysterious intersection of chance and a ready mind. The French chemist Louis Pasteur, a titan of the very field Fleming was working in, articulated this perfectly when he said, "Dans les champs de l'observation, le hasard ne favorise que les esprits préparés." In the fields of observation, chance favours only the prepared mind. Fleming's laboratory may have been messy, his methods at times haphazard, but his mind was meticulously prepared. It was prepared by his previous work with lysozyme, by his deep knowledge of bacteriology, and by an innate, unteachable curiosity that compelled him to look closer at an anomaly rather than discard it. The spore that drifted into his lab was pure chance, a random event in a sea of infinite possibilities. But the discovery of penicillin was not. It was the result of that chance event landing in the one environment, the one specific mind, that could recognize its immense and beautiful potential. So, as we begin our journey towards sleep, let us hold this gentle image in our minds. A forgotten glass dish, a tiny bloom of mold, and a quiet moment of noticing that would ripple outwards, saving countless lives and changing the course of human history. It reminds us that sometimes the most wondrous things are not found in the answers we are rigorously seeking, but in the questions we never thought to ask, waiting patiently in the silent, overlooked corners of our world. That state of quiet readiness, of a mind prepared to welcome the unexpected, is a delicate and subtle thing. But serendipity does not always arrive as a silent whisper in a dusty lab. Sometimes it comes with a sudden, surprising warmth, a plume of acrid smoke, and the unmistakable smell of a mistake that is, against all odds, a miraculous success. We drift now from the microscopic battlefields of London to the cluttered, chaotic workshops of mid-19th century America, where a man named Charles Goodyear was consumed by a single, maddening obsession: rubber. Natural rubber, harvested from the milky sap of trees, was a wonder material, but it had a fatal flaw. In the summer heat, it would melt into a sticky, foul-smelling glue, and in the winter cold, it would freeze into a brittle, useless solid. Goodyear was convinced that there was a way to stabilize it, to tame it, and he dedicated years of his life to this quest, driving his family into poverty, mixing the sticky gum with every substance he could imagine, from salt and pepper to witch hazel and ink. His experiments were relentless, methodical, and entirely unsuccessful. The discovery, when it finally came, was not the result of his careful method, but of a moment of pure, unadulterated clumsiness. In 1839, in a moment of agitated conversation, he accidentally dropped a piece of his latest experimental rubber, one mixed with sulfur, onto a searingly hot cast-iron stove. He expected it to melt into the usual puddle of goo, but instead, it charred. It cooked, like a piece of leather. When he scraped it off, he found that the rubber was no longer sticky or soft. It was tough, firm, and elastic, and it remained so whether it was heated or cooled. After years of tireless logical searching, the solution had come to him through a simple, foolish accident. He had discovered vulcanization. This was a different kind of serendipity from the one that graced Alexander Fleming. It was a discovery born not of quiet, patient observation, but of frantic, messy persistence colliding with a moment of chance. Goodyear's mind was certainly prepared, saturated with the problem of rubber, but the universe did not reward his calm contemplation. It rewarded his chaotic energy, his refusal to give up, by turning one of his countless failures into a transformative breakthrough. The process of vulcanization, understood in the language of chemistry, is a small miracle of architecture. The heat from the stove provided the energy for the sulfur atoms to build tiny, strong bridges between the long, tangled chains of rubber molecules. The polymers, these sulfur crosslinks, held the chains together, preventing them from sliding past one another when hot, and from locking rigidly in place when cold. The accident on the stove had forged a new and stable molecular city from the chaotic sprawl that had existed before, creating the durable, versatile material that would pave the way for tires, hoses, and 1,000 other inventions that would build the modern world. It is a powerful reminder that sometimes The path to discovery is not a straight line, but a messy, wandering journey where the destination is found only when we stumble. And yet, serendipity can also arrive with a gentle touch in a moment of complete and utter normalcy to someone who isn't even looking for anything. Let us travel forward in time to the year 1945. An engineer named Percy Spencer is working for the Raytheon Company, building magnetrons, the high-powered vacuum tubes that generate the microwaves used in radar systems. One day, he is standing in front of an active radar set, testing a new tube, when he notices a strange and pleasant sensation. A candy bar in his pocket, a simple peanut cluster bar, has begun to melt into a warm, gooey mess. Unlike Goodyear, Spencer was not wrestling with a grand problem. He was simply a curious man in the presence of a powerful new technology. His mind, the mind of a self-taught engineer with over 100 patents to his name, immediately began to connect the dots. The microwaves from the magnetron must have produced this heat. He tested his hypothesis, first by placing some popcorn kernels near the tube, which soon began to pop and dance around the lab. His next experiment, with a whole egg, exploded in the face of a skeptical colleague. It was clear that these invisible waves were a powerful and efficient source of heat. The happy accident of a melted candy bar led directly to the invention of the microwave oven, a device that would fundamentally change the landscape of the human kitchen. The science, when we pause to visualize it, is beautifully simple. The microwaves are a form of light, tuned to a frequency that is particularly good at shaking water molecules. Imagine the tiny water molecules in a piece of food as countless little dancers. The microwave energy acts as an irresistible rhythm, forcing them to spin and twist back and forth, billions of times per second. This frantic dance creates friction, and that friction creates heat, cooking the food from the inside out. Percy Spencer's serendipity was the quietest of all. He wasn't looking for anything. He wasn't even observing a failed experiment. He was just a man at work who noticed an anomaly, a gentle warmth in his pocket, and had the prepared mind to ask why. And so, from the violent heat of a forgotten stove and the invisible warmth of a radar tube, our world was remade, reminding us that the universe has potential locked away in every substance, in every invisible wave, just waiting for a clumsy drop or a melted chocolate bar to set it free. From the transformative power of a sudden and accidental spark of heat, we now turn our minds to the quiet, subtle magic of things that refuse to hold, things that fail to cohere in the way they were designed to. Our story drifts from the dramatic flair of a vulcanized material to the almost apologetic utility of an adhesive that wasn't strong enough, a perfect illustration that serendipity can be found not just in spectacular success, but in the gentle grace of a beautiful failure. In the year 1968, a scientist at the 3M company named Spencer Silver was on a quest for the opposite of failure. He was trying to create an exceptionally strong adhesive for use in the aerospace industry, a glue so powerful it could hold together the components of an aircraft. He mixed new formulations, tested their properties, and one day he produced something entirely unexpected. It was an adhesive, but it was pitifully weak. It was composed of microscopic, indestructible acrylic spheres that were sticky, yet they only made a light, temporary contact with any surface they touched. You could stick it to a piece of paper and then peel it away effortlessly, without leaving a residue, and you could do this again and again. By the standards of his project, it was a useless creation. And yet, Silver was captivated by its unique, paradoxical nature. He championed his peculiar, weak glue within the company for years, demonstrating its properties to anyone who would listen, but no one could conceive of a use for it. It was, for a long time, a solution without a problem, an answer waiting for a question that had not yet been formed. This is a profoundly different flavor of serendipity. It is not the sudden flash of insight from a single event, but the slow, patient belief in the value of an anomaly. Silver's mind was prepared not just to notice the accident, but to hold on to it, to protect it from the dismissal of his peers, trusting that its purpose was simply hiding. That purpose would arrive, as it so often does, in a completely unrelated context, in the mind of another. Art Fry, a fellow engineer at 3M, was a singer in his church choir. He was perpetually frustrated by the small slips of paper he used to mark the hymns in his book. They would constantly fall out or get lost. One day, during a particularly dull sermon, his mind began to wander, and it drifted to a seminar he had once attended, where his colleague Spencer Silver had demonstrated his strange, unloved adhesive. A spark ignited in Fry's mind. That weak, reusable glue would be the perfect bookmark. It would hold its place gently, without damaging the delicate pages of his hymn book, and could be moved as needed. The solution without a problem had finally met the problem without a solution. This was the birth of the Post-it note, a product that would change the landscape of offices, schools, and homes around the world. It was a discovery born of a collaborative serendipity, a beautiful dance between two prepared minds, one who created the unexpected thing, and another who, through his own unique experience, finally gave it a name and a home. Sometimes, however, the universe presents us with a failure so complete and so mysterious that the discovery lies not in finding a new use for it, but in the simple act of figuring out what went wrong. Our story now moves to a DuPont laboratory in 1938, where a chemist named Roy Plunkett was working with gases to create a new, non-toxic refrigerant. He and his assistant had prepared a canister of a gas called tetrafluoroethylene, which they had cooled and pressurized into a liquid. The next morning, they attached the canister to their apparatus and opened the valve, but nothing came out. The pressure gauge read 0. To all appearances, the canister was empty. Yet, its weight was unchanged. It felt just as heavy as it had when it was full of the precious gas. It was a confounding, frustrating puzzle. A lesser mind might have discarded the faulty cylinder and started over, but Plunkett's curiosity was piqued. Where had his gas gone? He and his assistant eventually decided to saw the heavy metal canister in half. When they finally pried it open, they looked inside to find not a gas, not a liquid, but a strange, waxy, pearly white powder. Through some unknown process, the individual gas molecules, the monomers, had spontaneously joined together inside the canister, forming a long, stable chain, a polymer. This new substance was astonishing. It was resistant to nearly every chemical. It could withstand extreme heat and cold, and it was one of the most slippery materials known to science. This was the accidental birth of polytetrafluoroethylene, better known to the world by its trade name, Teflon. Plunkett was not trying to invent a non-stick coating. He was just trying to find his missing refrigerant. The serendipity was a reward for his refusal to walk away from a mystery. He had stumbled upon a fundamental process of polymerization, catalyzed by the iron from the inside of the tank, a process that created the incredibly strong and stable bonds between carbon and fluorine atoms that give Teflon its remarkable properties. From a failed adhesive that sticks too little, to a failed gas that created a substance that refuses to let anything stick to it at all, we see how the world can be enriched by the things that do not go according to plan. They whisper to us a gentle and comforting truth, that even in our own imperfections and failures, a unique and beautiful purpose may just be waiting to be found. Just as a failed glue found its purpose in a gentle touch, and a vanished gas found its calling in a surface that nothing could touch, other laboratory mistakes have found their way into our lives, not through what they could do, but through how they could be perceived, through an unexpected whisper to our senses of taste and of sight. We drift now from the tangible world of materials to the ethereal realm of perception, to a time when our world of flavors and colors was about to be unexpectedly and permanently brightened. Our story begins in 1879, in the laboratory of a chemist named Konstantin Fahlberg at Johns Hopkins University. He was deeply immersed in his work, experimenting with the complex derivatives of coal tar, that sticky, black, and foul-smelling residue left over from the production of coal gas. It was messy, industrial work, far removed from the culinary arts. One evening, after a long day in the lab, he returned home for dinner. Lost in thought, he had forgotten the simple, cardinal rule of the laboratory: to wash his hands before leaving. As he sat down to eat, he picked up a bread roll, and upon lifting it to his lips, he was startled by a wave of sweetness. A profound and lingering sweetness that was unlike anything he had ever tasted. It was not the roll. He tasted his thumb, and the sweetness was even more intense. It was coming from him, from the chemical residue of his day's work with the black, grimy tar. He rushed back to his lab and began tasting every beaker and vial on his bench until he found the source. A compound he had synthesized called benzoic sulfamide. Through a simple act of absent-mindedness, he had discovered saccharin, the world's first artificial sweetener. This moment of serendipity is a beautiful bridge between two worlds that should never have met. The gritty, industrial landscape of 19th century chemistry and the most intimate, biological experience of taste. Nearly a century later, history would gently repeat itself. In 1965, a chemist named James Schlatter was working to create a new drug to treat stomach ulcers. He had synthesized a compound, a simple combination of 2 amino acids, and in a moment that echoed Fallberg's, he licked his finger to pick up a piece of weighing paper. Instantly, he was struck by the same surprising, overwhelming sweetness. This was the discovery of aspartame. Both of these world-changing discoveries came from a minor breach in protocol, a moment of human fallibility that allowed the hidden properties of a molecule to cross the threshold from the laboratory bench to the human tongue. The science behind this sensory surprise is a beautiful story of molecular happenstance. Our tongues are covered in taste receptors, microscopic structures that are shaped to fit specific molecules, like a lock designed for a particular key. When a sugar molecule dissolves in our saliva, it fits perfectly into the sweet receptor, sending a signal to our brain that we are tasting something sweet. By sheer, random chance, the molecules of saccharin and aspartame, created for entirely different purposes, happen to have a shape that could also fit into that lock. In fact, they fit so perfectly, so snugly, that they trigger a signal hundreds of times stronger than sugar, a phenomenon of pure, accidental molecular mimicry. The senses, however, are not limited to taste. A similar story of accidental beauty, also born from the unpromising sludge of coal tar, was waiting to unfold for the sense of sight. Our journey takes us to London, in the spring of 1856. A brilliant 18-year-old chemistry student named William Henry Perkin had set up a simple laboratory in his home, driven by an ambitious goal. He hoped to synthesize quinine, the only known treatment for malaria, a scourge of the British Empire. His plan, based on the theories of the day, was to try to produce this complex natural molecule from a simpler derivative of coal tar. His experiment was a resounding and unequivocal failure. Instead of the clear crystals of quinine, his beakers were left with a thick, dark, sticky muck. As he began the tedious process of cleaning his glassware with alcohol, he noticed something extraordinary. The black sludge dissolved not into a muddy brown, but into a breathtakingly beautiful, vibrant purple solution. He had accidentally created the world's first synthetic dye. He named it Mauvane, or simply Mauve. This moment was the mirror image of Fallberg's discovery. Both men had started with the same messy, unpromising substance. Both of their experiments had failed to achieve their intended goals. But where one failure revealed an invisible taste, the other revealed a visible, luminous color that would change the world. Before Perkin's discovery, the color purple was rare and impossibly expensive, extracted laboriously from tiny sea snails and reserved for the robes of emperors and kings. Perkin's accident made the color available to everyone, launching a fashion craze known as the mauve measles, and more profoundly, giving birth to the entire synthetic chemical industry, which would go on to produce everything from perfumes to explosives. And so, as our minds begin to settle, we can reflect on how the very world we perceive, the sweetness on our tongues and the colors that delight our eyes, has been painted and flavored by these gentle accidents. They remind us that even from the murkiest of failures, a light of unexpected beauty can emerge, coloring our world in shades we never could have imagined. From the accidental harmony between a laboratory molecule and our external senses, we now turn our gaze inward, to the vast, uncharted ocean of our own biochemistry, where a substance sent to one destination can be carried by unseen currents to an entirely unexpected shore. The human body is not a simple machine with straightforward levers and pulleys. It is a landscape of such staggering complexity that we are still, in many ways, only just beginning to draw its maps. And some of the most important features on those maps have been charted not by deliberate exploration, but by medical voyagers who, while searching for a new route to one territory, stumbled upon an entirely new continent. In the early 1990s, the pharmaceutical company Pfizer was conducting clinical trials for a new drug called sildenafil. Its intended purpose was to treat hypertension and angina, a type of chest pain caused by reduced blood flow to the heart. The logic was sound. The drug was designed to be a vasodilator, to gently relax and widen blood vessels, thereby increasing blood flow and easing the strain on the heart. But in practice, the results were disappointing. The drug had a negligible effect on angina. As the researchers prepared to abandon the project, however, they began to notice a pattern in the reports from the male participants in the trial. The drug was indeed dilating blood vessels, but it was doing so with remarkable efficiency in a region far from the heart, producing a very specific and very pronounced side effect. The discovery was initially awkward, a curious footnote in a failed trial, but its significance soon became clear. The key they had designed for the lock on the heart's coronary arteries happened to fit, with even greater perfection, a different lock entirely. The failed heart medication was reborn as Viagra, a drug that would not only transform the treatment of erectile dysfunction, but would also profoundly change social conversations about health, aging, and quality of life. This is a powerful lesson in scientific humility. It reminds us that the body is a deeply interconnected system, a web of pathways and messengers so intricate that a single chemical signal can echo in unforeseen places. The same story, with a different substance, had already unfolded decades earlier. In the late 1950s, scientists were testing a potent new vasodilator called minoxidil, also intended to treat high blood pressure. In this case, the drug worked remarkably well for its intended purpose, but it came with a side effect that was, for the researchers, a bizarre and confounding curiosity. Patients being treated with the drug began to grow hair, not just on their heads, but on their cheeks, their foreheads, their arms. The same mechanism of action, the widening of blood vessels to increase blood flow that was lowering their blood pressure, was also reawakening dormant hair follicles. For years, this was seen as a problematic side effect to be managed, but eventually, a prepared mind recognized its potential. The potent blood pressure pill was reformulated into a topical solution, a lotion that could be applied directly to the scalp. And Rogaine entered the world, another billion-dollar drug born from an unexpected biological detour. These discoveries invite us to visualize the body not as a blueprint, but as a thriving, wild ecosystem. A medicine entering the bloodstream is like a river diverted for irrigation. You may intend for it to water a specific crop, but along the way, it may seep into the soil, replenishing the water table, causing wildflowers to bloom in a distant, forgotten meadow. The scientific field that studies these intricate journeys is known as pharmacokinetics, a gentle word that describes the epic voyage of a single molecule through the body. How it is absorbed into the bloodstream, how it is distributed to different tissues and organs, how it is chemically altered by the liver, and how it is finally excreted. This journey is never a simple A to B transit. The molecule is tumbled through the turbulent currents of the blood. It binds to countless different proteins, and it interacts with a dazzling array of cellular receptors. It is a path of 1,000 possibilities, and it is in this complexity that the potential for serendipity thrives. The molecules of sildenafil and minoxidil were simply following their chemical nature, but in the unique and mysterious landscape of the human body, their nature led them to a purpose their creators had never dreamed of. As we conclude our first explorations into the world of happy accidents, we are left with this deep and comforting sense of wonder at our own physical selves. We inhabit a body that is still, in so many ways, a terra incognita, a world of hidden connections and surprising responses. To be in a body is to be a living mystery, a vessel of uncharted currents, where a journey begun with one intention may always, with the grace of serendipity, find a new and more beautiful destination. And as we rest now, we can feel the gentle rhythmic currents within us, the steady beat of the heart, and the slow tide of the breath, and trust in the quiet wisdom of this vessel that carries us through the night. As we drift from the hidden pathways within our own bodies, Our journey now carries us into the deeper darkness of the surrounding world, into a laboratory where a new kind of light, an invisible and penetrating light, was about to pierce the veil of solid matter for the very first time. This marks the beginning of our descent into the more profound and awe-inspiring accidents of science, into the moments that did not just give us a new product or a new medicine, but fundamentally rearranged our entire perception of reality. Our story begins on a cold evening in November 1895 in the darkened physics laboratory of Wilhelm Röntgen in Würzburg, Germany. The room is steeped in a profound, inky blackness. Röntgen is experimenting with a Crookes tube, a simple glass bulb from which most of the air has been pumped out. When he passes a high-voltage electric current through the tube, it produces a stream of electrons known as cathode rays, causing the glass itself to glow with a faint, eerie light. But Röntgen is not interested in that visible light. He has meticulously covered the entire tube with a shield of heavy black cardboard, ensuring that no light whatsoever can escape into the room. His goal is to study the cathode rays in total darkness. As he activates the coil, sending a current through the sealed tube, his eye is caught by a flicker of light from across the room. On a small bench a few feet away, he sees a faint, ghostly green shimmer, a pale and ethereal luminescence where no light ought to be. In that moment, the world held its breath. The source of the shimmering was a small screen coated in a chemical called barium platinocyanide, a material he had been planning to use for a later experiment. It was a fluorescent material, meaning it had the ability to absorb energy and re-emit it as visible light. But what energy could it possibly be absorbing? The room was dark. The tube was sealed. He turned off the current to the tube, and the laboratory was plunged back into absolute blackness. The shimmering vanished. He turned the current back on. The ghostly green light reappeared in the same spot, a silent, luminous phantom. A deep sense of wonder, and perhaps a touch of fear, must have filled him as he realized he was in the presence of something entirely new. He began to investigate with a feverish intensity. He took the fluorescent screen into the next room, and still it glowed when the tube was activated. He placed objects between the tube and the screen. A book, a block of wood. The screen still glowed. These unknown rays were passing through solid objects as if they were mist. Then came the moment that would echo through history. He held a small disc of lead in front of the screen and saw its dark shadow cast upon it. And as he held it, he saw another, fainter shadow, a shadow within the shadow of his own hand. He saw the delicate, unmistakable outlines of the bones of his fingers and thumb. In that instant, he became the first human being to look inside his own living body, to see the hidden architecture of his own skeleton. The solid, familiar world had dissolved into a transparent ghost. Because he did not know what these rays were, he gave them a simple, humble name. X-rays, with the X standing for unknown. This serendipitous glance at a shimmering screen was one of the most profound turning points in the history of science. It was the discovery that our five senses, which we trust so implicitly to define our reality, are in fact profoundly limited. The world was not as it seemed. It was threaded through with invisible energies, with silent messages that we had never before had the capacity to perceive. We can visualize the full range of these energies, the electromagnetic spectrum, as a vast and magnificent piano keyboard stretching out in both directions for miles. In the very middle of this immense keyboard sits one single, tiny octave of keys. This is the octave of visible light, the familiar colors of the rainbow, the only part of this grand instrument our eyes are built to hear. Röntgen, in his darkened room, had accidentally and unknowingly played a chord in a much higher, much more energetic octave, and the fluorescent screen had acted as a translator, allowing his human eyes to see the result. His discovery threw open the doors to all the other invisible octaves. The low, resonant notes of radio waves, the warmth of infrared, the sharp, unseen light of the ultraviolet. We learned, in that moment, that we are swimming in an immense ocean of information to which we were previously blind and deaf. The fluorescence of that simple screen was the key. The material itself was prepared to see what Röntgen was not, absorbing the high energy of the X-rays and releasing it as a gentle, visible glow, a whisper from the unseen world. And as we settle deeper into our own quiet darkness, we can feel a sense of awe for this vast, invisible reality that enfolds us. A universe rich with hidden light and silent energies, a world whose deepest secrets are sometimes revealed not by a great search, but by a faint and accidental glimmer in the dark. That accidental glimmer in the dark revealed a universe filled with invisible energies we could create, but it soon led to an even more profound revelation, that the universe, on its own, had been speaking in this silent, energetic language all along, not from a glass tube, but from the very stones beneath our feet. Our story now drifts to Paris, in the year 1896, just a few months after Röntgen's astonishing announcement had electrified the scientific world. A physicist named Henri Becquerel, like many others, was captivated by the mystery of X-rays. He developed a hypothesis, a logical but incorrect idea, that connected this new phenomenon to an old one. He theorized that the production of X-rays might be linked to phosphorescence, the enchanting ability of certain materials to absorb sunlight and then glow softly in the dark. To test this, he chose a phosphorescent material he had long studied: uranium salts. His experimental design was simple. He would take a photographic plate, wrap it securely in thick black paper to protect it from light, place the uranium crystals on top, and leave the entire arrangement out in the brilliant Parisian sun. His hope was that the sunlight would cause the uranium to phosphoresce, and in the process, emit X-rays that would penetrate the paper and fog the plate inside. And when he performed the experiment, it worked perfectly. The developed plate showed a clear silhouette of the crystals. His hypothesis, it seemed, was correct. But then, serendipity intervened in the form of the weather. For several days, at the end of February, the skies over Paris were grey and overcast, and Becquerel could not continue his experiments. Growing impatient, he took his carefully prepared photographic plate, with the uranium salts still resting on top, and placed the whole assembly inside a dark, quiet desk drawer to await a sunnier day. For several days, it rested there in absolute, undisturbed blackness. At some point, driven by a flicker of curiosity or perhaps just a desire to clear his workspace, he decided to develop the plate anyway, expecting to see a very faint, weak image at best. Instead, he was stunned to find that the image was incredibly sharp, dark, and clear, even more so than in his experiments conducted in bright sunlight. A profound realization washed over him. The sun was irrelevant. The phosphorescence was a red herring. The energy was not coming from an external source to be absorbed and re-emitted. It was coming from within the uranium itself, a spontaneous and ceaseless emission, a silent, invisible light that had been pouring out of the mineral in the deep, unwavering darkness of his drawer. He had discovered radioactivity, the universe's own internal fire. This accidental discovery was a philosophical earthquake. It suggested that matter, which had been seen as largely passive and inert, could possess its own deep wellspring of energy. It was as if the stones themselves had a secret, dynamic life, an internal clock that had been ticking away since the dawn of time. This single, beautiful accident was the doorway into a new and dangerous world, and it was a young Polish scientist in Paris, Marie Curie, who would have the courage to walk through it. She took Becquerel's strange observation and, with her husband Pierre, transformed it into an entirely new field of science. She coined the very term radioactivity and began a methodical search for other elements that possessed this strange internal power. Her work was the opposite of a happy accident. It was a grueling, heroic labor. She and Pierre spent 4 years in a leaky, unheated shed, processing tons of raw pitchblende ore, a Herculean task of chemical refinement, to isolate mere fractions of a gram of 2 new, powerfully radioactive elements: polonium, which she named for her beloved homeland, and radium. They would work late into the night, and she would later recall the beauty of their discovery, how the small glass vials containing the concentrated radium would glow in the dark with a soft, ethereal, blue-green light, a visible manifestation of the powerful, unseen rays that Becquerel had stumbled upon. His serendipity was the question. Their tireless work was the beginning of the answer. The answer, in the language of physics, lies deep within the heart of the atom. For most atoms, the central nucleus is a stable, tightly bound family of protons and neutrons. But in very large, heavy elements like uranium and radium, the nucleus is overcrowded and unstable. Radioactivity is the process of this unstable nucleus spontaneously trying to find peace by casting off a particle or a burst of energy, transforming into a new, lighter element in a process called radioactive decay. Each radioactive element has its own timescale for this decay, its own internal clock, ticking away over seconds or years or the lifespan of the Earth itself. And so, from a stretch of cloudy Parisian weather and a forgotten plate in a dark drawer, our understanding of matter was forever changed. We learned that the seemingly solid ground we stand on is not truly solid, but is infused with a slow, powerful, and ancient energy, a quiet fire at the very heart of the world. The discovery that matter itself could hold a steady, silent fire was a wonder. But the cosmos held a different kind of surprise, not a constant glow from the Earth, but a strange and perfect rhythm from the heavens, a cosmic heartbeat that was so precise, so unnatural, it seemed for a time to be a message from another world. We travel now to the damp fields of Cambridge, England, in the year 1967. A brilliant and determined young graduate student from Northern Ireland named Jocelyn Bell Burnell is putting the finishing touches on a massive new radio telescope she had spent the last 2 years helping to build. Her project was to use this new instrument, a sprawling 4.5-acre web of wires and poles, to study quasars, the distant, flickering, radio-bright hearts of ancient galaxies. Her task was a laborious one: to analyze, by hand, the 100 feet of paper chart that the telescope produced every single day, looking for the telltale scintillations, the twinkling of these far-off objects as their signals passed through the solar wind. For months, it was a monotonous task, her eyes scanning the jagged, inky lines for a familiar pattern. But then, one day in August, she noticed something else. It was, in her own words, a bit of scruff, a faint, messy-looking signal that didn't look like a quasar, nor did it look like the random crackle of terrestrial interference. It was a signal that seemed to appear and disappear, and she marked it with a question mark and moved on. But the signal returned. A month later, she saw it again, coming from the same patch of sky. This time, she was able to record it with a faster chart speed, and what she saw made her heart quicken. The scruff was not messy at all. It was a breathtakingly regular series of sharp, distinct pulses, arriving with a precision that was almost unbelievable. One pulse, every 1.337 seconds. Again, and again, and again. The rhythm was more perfect than a human heartbeat, as steady as the most accurate atomic clock on Earth. She brought the finding to her supervisor, Anthony Hewish, and together they explored every possible explanation. It could not be from Earth. The signal kept perfect time with the stars, meaning it was moving across the sky as our planet rotated. It could not be an equipment malfunction. Other telescopes confirmed its existence. The signal was so regular, so seemingly artificial, that they could not, at first, dismiss the most fantastical possibility of all. They half-jokingly, and in complete secrecy, nicknamed the source LGM-1 for Little Green Men. For a few tantalizing weeks, they lived with the quiet, thrilling possibility that Jocelyn Bell Burnell, in her patient, methodical scanning of the sky, had accidentally stumbled upon a beacon from an extraterrestrial civilization. The key to solving the mystery was, as is so often the case in science, to find more examples. Just before Christmas, Bell Burnell, working late and alone in the cold observatory, found a second signal, another perfectly regular series of pulses coming from a completely different part of the sky. Soon after, she found a third, and then a fourth. The Little Green Men hypothesis, as thrilling as it was, began to fade. It seemed incredibly unlikely that 4 separate alien civilizations, scattered across the galaxy, would all decide to contact Earth at the same time, using the same strange, pulsing method. The explanation had to be a natural one, but a natural phenomenon of a kind no one had ever seen before. The answer came from the realm of theoretical physics. Scientists realized that this perfectly regular pulse could be produced by a neutron star, the bizarre, super-dense corpse of a massive star that has exploded as a supernova. Imagine an object with more mass than our Sun, crushed by its own gravity into a sphere no bigger than a city. It is so dense that a single teaspoon of its material would weigh more than all the mountains on Earth. As this stellar remnant collapses, its rotation speeds up, just as an ice skater spins faster when she pulls in her arms. These neutron stars can spin on their axis hundreds of times per second, and as they spin, they emit powerful focused beams of radio waves from their magnetic poles. The object Jocelyn Bell Burnell had found was not a signaling alien, but a cosmic lighthouse. As the dead star spins, its beams of energy sweep across the universe. If our small planet happens to lie in the path of one of those beams, our radio telescopes register a pulse every single time the beam sweeps past us. The serendipitous bit of scruff on a paper chart had revealed a new and wondrous class of celestial object. It was a discovery that replaced the simple fantasy of little green men with a far more profound and beautiful reality. The steady, rhythmic heartbeat of a distant, spinning star, a silent keeper of time in the vast, dark ocean of the cosmos. From the precise, rhythmic heartbeat of a single dead star, our journey now expands to its furthest possible horizon, to listen not to a solitary celestial object, but to the faint, persistent, and universal static that turned out to be the oldest sound in creation, the echo of the Big Bang itself. Our story unfolds not in a remote, pristine observatory, but in the rolling hills of Holmdel, New Jersey, in 1964. Two young radio astronomers at Bell Laboratories, Arno Penzias and Robert Wilson, had been given access to a magnificent and rather peculiar instrument, the Holmdel horn antenna. It was a massive, horn-shaped receiver, originally built to communicate with the first generation of satellites. With that project over, Penzias and Wilson were free to use it for pure astronomy, to map the faint radio signals emanating from the halo of our own Milky Way galaxy. But from the very beginning, they were plagued by a problem. A noise. It was a faint, steady, and incredibly persistent hiss. A low-level background static that was present no matter where they pointed the great horn in the sky. It was there at night, it was there during the day, it was there in the spring, and it was there in the winter. It seemed to come from everywhere and from nowhere. As dedicated scientists, they set about trying to eliminate this noise with a methodical and growing sense of frustration. They checked the wiring, they recalibrated the instruments, they rebuilt the amplifiers. The hiss remained. They considered every possible source. Could it be radio interference from nearby New York City? They pointed the horn directly at the city, and the noise did not get any louder. Could it be residual heat from the instrument itself? They cooled their receiver with liquid helium to just 4 degrees above absolute zero, the coldest possible temperature, and still, a faint hiss, equivalent to a temperature of about 3.5 degrees, stubbornly remained. Their investigation led them to the most famous and comical chapter of this story. Climbing inside the 20-foot maw of the antenna, they found that a pair of pigeons had taken up residence, coating the sensitive interior with what they would later describe in a scientific paper as a white dielectric material. They began to suspect that the warmth and mess from the birds might be the source of their maddening noise. So, they cleaned out the antenna, but the hiss persisted. They trapped the pigeons and released them 40 miles away, only to watch in dismay as the determined birds returned to their home a few days later. Finally, they resorted to what Penzias would only describe as a more direct and permanent solution to their pigeon problem. And still, after all that, the faint, infuriating hiss remained. This is a moment of sublime and beautiful absurdity. Two brilliant minds, armed with one of the most sensitive instruments on Earth, engaged in a battle of wits with a pair of pigeons, all while being completely unaware that they were on the precipice of the single greatest cosmological discovery of the 20th century. The solution to their mystery came not from an instrument, but from a simple telephone call. Penzias was talking to a colleague at another university who happened to mention the work being done by a group of theoretical physicists at nearby Princeton, led by a man named Robert Dicke. Dicke and his team were pursuing a grand idea. They had reasoned that if the universe had truly begun in an unimaginably hot, dense state, a Big Bang, then the explosive energy of that creation should not have simply vanished. It should still be present today, a faint, residual afterglow, an echo of that first fire. This ancient light, they calculated, would have been stretched and cooled by the 13.8 billion years of cosmic expansion, and should now be detectable as a faint, cold, background glow of microwave radiation, permeating all of space with a temperature of just a few degrees above absolute zero. As Penzias listened to this, the pieces of the puzzle fell into place with a thunderous crash. The Princeton team was building a special telescope to go looking for this very signal. But Penzias and Wilson had already found it. They just hadn't known what it was. The most annoying, persistent, and inexplicable noise in the history of radio astronomy was the sound of creation. It was the universe's first light, finally reaching us after a journey of nearly 14 billion years. That faint hiss was the oldest and most profound message we have ever received. A message not from a specific star or galaxy, but from the entire cosmos, whispering the story of its own birth. It teaches us a lesson in deep humility, that sometimes the greatest secrets of the universe are not hidden in far-off exotic places, but are all around us, all the time, disguised as mundane noise, waiting patiently for us to finally clear away the pigeons and truly listen. Listening to that ancient static from the dawn of time gave us the story of the universe's birth. But when we turned our gaze to the great, spinning cities of stars that formed much later, a new and deeper mystery emerged, not from a sound, but from a silent, stubborn motion that suggested the luminous world we see is only a tiny fraction of what is truly there. Our story now focuses on the patient, meticulous work of a remarkable astronomer named Vera Rubin. In the 1960s and 70s, at a time when cosmology was dominated by theory and observation was often considered secondary, Rubin was a staunch believer in the power of data. She wanted to look, not just to think. Working with her colleague Kent Ford and his advanced new spectrometer, she set out to do something that had never been done with such precision before: to measure the speed of the stars within our nearest major neighbor, the Great Andromeda Galaxy. The expectation was simple, based on the laws of gravity that have governed our understanding of the cosmos since Isaac Newton. In a spinning system like a galaxy, most of the mass, and therefore most of the gravitational pull, is concentrated in the bright, dense center. The stars in the outer regions of the galaxy should behave just like the outer planets in our solar system. Being farther from the central mass, they should feel a weaker gravitational pull and should be moving much more slowly. Mercury orbits the Sun at a blistering pace, while distant Neptune plods along in a slow, majestic arc. Rubin expected to see the same graceful slowing of speeds in the stars at Andromeda's edge, but that is not what she saw. Her data, collected over many long nights at the observatory, was clear, unambiguous, and completely wrong. The stars at the galaxy's edge, far from moving more slowly, were orbiting just as fast as the stars much closer in. She checked her data, recalibrated her instruments, and looked again. The result was the same. She and Ford then turned their attention to other galaxies, and in every single one, they found the same baffling phenomenon. The galactic rotation curves, the graphs of stellar speed versus distance, were mysteriously flat. The galaxies were spinning far too fast. According to all known laws of physics, the stars on the outskirts should have been flung off into the void of intergalactic space, like children flying off a carousel that is spinning too quickly. The visible matter of the galaxy, all the billions of brilliant stars she could see, was not providing nearly enough gravitational glue to hold these rapidly spinning systems together. This was not a sudden, single accident, like a fogged plate or a melted candy bar. This was serendipity as a slow, creeping, and undeniable anomaly. A discovery born not of a lucky glance, but of a persistent, courageous refusal to ignore what the data was screaming. Vera Rubin was forced to a conclusion that was as profound as it was revolutionary. There had to be something else out there, something more. The only way these galaxies could hold themselves together was if they were embedded in a vast, invisible halo of some unknown substance, a substance that possessed an immense gravitational pull but did not emit, absorb, or reflect any light. This mysterious, unseen stuff was given a simple and evocative name: dark matter. It is a ghostly scaffolding upon which the luminous structures of our universe are built. We cannot see it. We cannot touch it. We have never detected it directly in a laboratory. We only know it exists because we can see its powerful, silent, gravitational grasp on the things we can see, the very stars that Vera Rubin so carefully observed. To understand this, imagine watching that spinning carousel at night, but you can only see the bright, colourful lights on the children's clothes. If you saw the lights on the outer edge moving just as fast as the lights near the centre, you would have to conclude that something invisible was holding them in place, a ghostly set of hands providing the extra grip needed to keep them on their circular path. This is what Rubin saw in the stars. Her discovery, while slow to be accepted, fundamentally changed our cosmic inventory. The ordinary matter that makes up you, me, the Earth, the Sun, and all the brilliant stars in all the galaxies accounts for only about 5% of the total mass and energy of the universe. Dark matter, this mysterious substance Rubin's data uncovered, makes up about 27%. The rest is an even stranger phenomenon called dark energy. And so, just as Röntgen's rays taught us that our eyes are blind to a world of invisible light, Vera Rubin's spinning galaxies taught us that we are blind to the vast majority of the matter that makes up our cosmos. We live on a luminous island, unaware that it is merely foam on the surface of a vast and deep invisible ocean, a silent, unseen presence that gracefully and powerfully holds our entire universe together in its ghostly embrace. From the ghostly, cosmic scaffolding that holds the galaxies together, our story now returns to Earth, to the humble workbench of a chemist who, in searching for a substitute for a simple natural lacquer, accidentally forged a new kind of matter, a substance that would become the tangible, malleable scaffolding of our modern, human world. At the dawn of the 20th century, the world was becoming electric. Great networks of copper wires were spreading across nations, carrying this new and magical force into homes and factories. But electricity needed to be contained, to be insulated, and the best material for the job was shellac, a simple resin painstakingly scraped from the secretions of the tiny lac bug in Southeast Asia. It was a natural, effective, but finite resource, and as the electrical age boomed, the search for a synthetic substitute became a matter of great industrial urgency. It was this challenge that captivated the mind of Leo Baekeland, a brilliant and already wealthy Belgian-American chemist. He began his work in 1907, in his home laboratory in Yonkers, New York, experimenting with two common byproducts of coal tar, phenol and formaldehyde. He knew that when these two chemicals were mixed and heated, they produced a hard, resinous substance. But it was a messy, uncontrollable reaction, a nuisance that tended to permanently gum up his beakers and flasks. Other chemists had encountered this insoluble gunk for decades and had dismissed it as a useless, frustrating failure. But Leo Baekeland possessed a mind that was prepared not just to see an accident, but to embrace a problem. Where others saw a failed reaction, a chemical dead end, Baekeland saw the destination itself. He asked a different question. What if this hard, insoluble material wasn't the problem? What if it was the solution? His genius was in finding a way to tame this messy reaction, to control it. He designed and built a heavy iron vessel he called a buckylizer, a kind of chemical pressure cooker. He realized that if he controlled the reaction under high heat and intense pressure, he could produce the hard resin in a predictable way. More than that, he discovered he could mix the initial liquid resin with fillers like wood flour or asbestos, pour this mixture into a mold of any shape he desired, and then cook it in his bakellizer. The result was a substance the world had never seen before. It was hard, yet lightweight. It was a superb electrical insulator. It was resistant to heat, and once it had been set, it could not be melted or dissolved. He had not just created a substitute for shellac, he had created a new world of material possibility. He called his invention Bakelite, and it was the world's first entirely synthetic plastic. The serendipity here was a profound shift in perspective. It was the insight to see the promise in the nuisance, the potential in the problem. The chemistry at work was a process of creation. The small, simple molecules of phenol and formaldehyde are like short pieces of thread, The heat and pressure in the baculizer acted as a loom, weaving these threads together into a vast, three-dimensional, and heavily cross-linked molecular fabric. The result was a thermosetting polymer. Unlike other plastics that can be melted and reformed, bakelite, once set, is locked into its shape forever. This accidental embrace of a failed reaction was a moment of fundamental philosophical importance. For the entirety of human history, we had been users of the materials given to us by nature. We carved wood, we chipped stone, we smelted metal. But with bakelite, humanity had, for the first time, created a new category of matter from simple chemical building blocks, a substance that did not exist anywhere in the natural world. This discovery was the catalyst for the age of plastics. The smooth, dark, and durable material was soon everywhere, forming the casings for radios and telephones, the gleaming handles of kitchenware, the colourful spheres of billiard balls, and delicate pieces of jewellery. By Keelan's accident, his decision to look closer at the gunk in his flask had unleashed a power of creation that would reshape our civilization. This moment can also be seen as a quiet, pivotal event in the dawn of a new geological epoch, the Anthropocene, an age defined by humanity's impact on the planet. The creation of novel and incredibly durable materials like plastics, substances that will persist in the geological record for millions of years, is one of the key markers of this new age. And so, as our minds drift, we can contemplate this profound story of creation. The simple desire to replace the work of a tiny insect led, through the embrace of a chemical mistake, to a power that would change the very fabric of our world, a quiet reminder that sometimes the greatest discoveries lie not in finding what is already there, but in learning to create what has never been. Just as a chemist's accident allowed us to synthesize new materials for the world around us, another chemist's accident would, a few decades later, reveal that a synthetic molecule could also unlock strange and profound new landscapes within the world of the mind. A journey that began, famously, with a dizzying bicycle ride home. Our story takes us to the city of Basel, Switzerland, in the year 1938. A meticulous and brilliant chemist named Albert Hofmann is working in the pharmaceutical laboratories of the Sandoz company. His research is focused on ergot, a fungus that grows on rye and other grains. Ergot has a long and complex history with humanity. It contains powerful alkaloids that have been used in midwifery for centuries, but can also cause outbreaks of madness and gangrene when it contaminates bread. Hoffmann's job was to isolate the active compounds from this fungus and synthesize new variations, hoping to create useful medicines. In the course of this work, he created the 25th substance in a particular series of derivatives. Its full name was lysergic acid diethylamide, which he abbreviated to the simple, clinical-sounding name LSD-25. He had hoped it might work as a circulatory and respiratory stimulant, but when tested on animals, it showed no remarkable effects, and the compound was shelved, forgotten in the vast chemical library of the company. 5 years passed. Then, on a spring day in 1943, for a reason he could never fully explain, Hofmann was overcome by what he would later call a peculiar presentiment, a strange and persistent feeling that this forgotten molecule might have other, undiscovered properties. Acting on this scientific intuition, a small serendipity in itself, he decided to synthesize a new batch of LSD-25. It was on that afternoon, Friday, April 16th, as he was performing the final stages of the purification, that he began to feel strange. A remarkable restlessness grew within him, accompanied by a slight dizziness. He was not ill, but the world felt subtly altered. He stopped his work and went home to lie down. As he closed his eyes, his mind was flooded with what he described as an uninterrupted stream of fantastic pictures, extraordinary shapes with intense, kaleidoscopic play of colours. After about 2 hours, the experience faded. His scientific mind immediately deduced the cause. He must have accidentally absorbed a minuscule, trace amount of the LSD he was working with, perhaps through the skin of his fingertips. To be a true scientist, he knew he had to confirm this hypothesis. 3 days later, on April 19th, a date now famous in history, he decided to perform a deliberate self-experiment. With his assistant by his side, he ingested what he assumed was a vanishingly small threshold dose. 250 micrograms, a mere speck of white powder. He had no way of knowing that LSD is one of the most potent psychoactive substances on Earth, and that this was, in fact, an incredibly powerful dose. Within the hour, the effects began to take hold, far more intensely than before. The world in his laboratory began to warp. Anxious, he asked his assistant to escort him home. As this was wartime, no cars were available, and so they set off on bicycles. This bicycle ride would become the stuff of legend. As he pedaled, the familiar streets of Basel began to dissolve into a surreal dreamscape. The road before him seemed to undulate like water. The buildings on either side breathed and buckled. His sense of time stretched and compressed. It was a frightening, overwhelming journey into the depths of his own consciousness. This was serendipity at its most intensely personal. The discovery was not happening in a petri dish or a distant galaxy. It was happening within him. And yet, even in the midst of this psychic storm, a part of his mind remained the calm, curious observer, taking mental notes on the complete transformation of his own reality. The science behind his terrifying and wondrous journey is a story of molecular deception. Our brains function as a vast, intricate network of neurons, communicating through chemical messengers called neurotransmitters. One of the most important of these is serotonin, a molecule that plays a crucial role in regulating our mood, our sensory perception, and our very sense of self. By an incredible accident of cosmic design, the LSD molecule that Hoffman synthesized has a shape that is almost identical to the serotonin molecule. It is a perfect counterfeit key. When it enters the brain, it fits neatly into the serotonin receptors, but it doesn't just deliver the normal message. It gets stuck in the lock, amplifying and scrambling the signals, tearing down the filters that normally allow our brains to create a stable, coherent reality from the chaotic flood of sensory information. Hoffman's accidental discovery threw open the doors of perception, revealing just how fragile our everyday reality is. It showed that the entire, solid-seeming world of our conscious experience is balanced on the delicate and beautiful architecture of a few simple molecules. From the kaleidoscopic journey sparked by an external chemical, our story now drifts deeper into the mind's own mysterious territory, to a place where the subconscious, in the quiet theatre of a dream, can offer up an image so powerful it solves a puzzle that has mystified the waking world of science. We journey back to the middle of the 19th century, a time of immense progress in chemistry. Scientists were beginning to understand the fundamental rules of how atoms combine to form molecules, but one substance, a common and vitally important one, refused to give up its secrets. That substance was benzene. Chemists knew its formula with certainty: C6H6. It was composed of 6 carbon atoms and 6 hydrogen atoms. The problem was the structure. All the prevailing theories suggested that carbon atoms should link together in long, open chains. But no matter how they tried to draw a chain of 6 carbon atoms, they could not find a stable arrangement that would also accommodate the 6 hydrogen atoms and explain benzene's peculiar chemical properties, most notably its strange and stubborn reluctance to react. The mystery of benzene was one of the greatest unsolved puzzles of the age, a chemical conundrum that occupied the waking thoughts of a German chemist named August Kekulé. Kekulé had already been visited by the serendipity of the subconscious once before. As a young man, he had been struggling with the very nature of chemical bonds when, riding on the top deck of a horse-drawn omnibus in London, he fell into a reverie. He later described how he saw atoms gambling before his eyes, forming into long chains, twisting and turning in a snake-like motion. That daydream provided him with the foundational insight for his theory of chemical structure, the very idea that carbon atoms could link to one another to form the backbone of organic molecules. It was a revolutionary leap forward for chemistry. Yet it still wasn't enough to solve the riddle of benzene. The answer would have to come from a deeper, more symbolic place. Years later, in 1865, Kekulé was a professor in Ghent, Belgium. One evening, he sat in his study, working on his textbook, but his mind would not focus. He turned his chair to the fireplace and began to doze. Once again, the atoms began their dance in his mind's eye. But this time, the vision was different. He saw the long, snake-like chains of atoms, writhing and twisting. And then, suddenly, one of the snakes seized its own tail in its mouth, and the ring that it formed began to whirl mockingly before his eyes. Kekulé awoke with a flash of lightning. He understood instantly. The snake biting its own tail was the Ouroboros, the ancient symbol of eternity and unity. And it was the solution to his problem. The 6 carbon atoms of benzene were not in a long, straight chain. They were in a closed loop, a perfect, elegant ring. The serpent had swallowed its own tail, and in that symbolic union, the puzzle was solved. This hexagonal ring structure perfectly accounted for benzene's formula, for its stability, and for all of its other strange chemical properties. Kekulé spent the rest of the night in a fever of excitement, working out the full implications of his dream vision. This was not the serendipity of a forgotten plate or a clumsy spill. This was a gift from the deepest, most ancient part of the human mind. His conscious mind was saturated with the problem, wrestling with the logical rules of chemical bonding. But it was his subconscious, free from these rigid constraints, that was able to make the creative leap. In the soft, symbolic language of a dream, it found a powerful archetypal image that perfectly mirrored the hidden structure of the molecule. The dream was not a random firing of neurons. It was the final, elegant step in a long and arduous process of thought, a beautiful marriage of logic and myth. The discovery of the benzene ring was a monumental event in the history of science. It unlocked the entire field of aromatic chemistry. This simple hexagonal ring is the foundational structure for hundreds of thousands of vital compounds. From the aniline dye that William Perkin had accidentally discovered, to powerful explosives, to life-saving pharmaceuticals, and even to the very building blocks of life itself. The amino acids that form our proteins, and the nucleic acids that form our DNA. And it all came from a moment of rest, a gentle doze in a chair by a warm fire. It is a profound and comforting reminder, as we too drift towards sleep, that our minds do not cease their work when we rest. They continue to search, to connect, and to dream, sometimes building a bridge of pure symbol between a waking question and a truth that can only be seen with the eyes closed. Just as a dream revealed the secret of a repeating chemical ring, our story now moves to the biological realm, to a mystery found not in a vision, but in the plain text of life itself, a strange, stuttering, repeating pattern in the DNA of microbes that, for years, was a mere curiosity before it was revealed to be an ancient and powerful tool. Our journey begins in 1987, in a laboratory at Osaka University in Japan. A team of scientists led by Yoshizumi Ishino is studying the genetics of the common bacterium, E. coli. As they meticulously sequence a particular gene, they notice something unusual in the surrounding DNA. It is a sequence of base pairs that is repeated, perfectly, 5 times. And in between these identical repeating segments are other, unique sequences of a similar length, which they call spacers. It is an oddity, a strange and ordered pattern in a place they did not expect to find one. They note its existence in their scientific paper, a small, unexplained observation, and move on. For more than a decade, that is all it remains. Our biological curiosity. Other scientists, studying other microbes, begin to find the same strange, repeating architecture in their genomes. The pattern is given a more formal, if still deeply unpoetic, name. Clustered regularly interspaced, short palindromic repeats, or CRISPR. But no one knows what it is for. It is a biological enigma, a piece of life's poetry written in a language that no one could yet read. The first great serendipitous leap towards understanding came in the early 2000s, from the patient, almost obsessive work of a Spanish scientist named Francisco Mojica. He had been captivated by these CRISPR sequences for years, convinced they must have an important function. At the time, new public databases of genetic sequences from thousands of organisms were becoming available online. Driven by a powerful hunch, Mojica began a tedious but crucial task. He started comparing the unique spacer DNA, the sequences that sat between the identical repeats in the bacteria, to all the other known DNA sequences in the databases. And he found the match. The spacer sequences were not random. They were perfect snippets of DNA from viruses, specifically from the bacteriophages, the ancient viral predators that hunt and destroy bacteria. This was the electrifying aha moment. The strange CRISPR region was not just a curiosity. It was a sophisticated, adaptive immune system. The bacteria were keeping a genetic record of their past infections. We can imagine it as a cellular library of mugshots. Each spacer was the captured fingerprint of a defeated viral enemy, stored away for future reference. The strange, stuttering pattern was, in fact, an ancient and elegant archive of immunological memory. This discovery sparked a flurry of research around the world, as scientists raced to uncover how this immune system actually worked. The full mechanism, pieced together by many different labs, is a marvel of natural engineering. When a new virus attacks a bacterium, a set of specialized proteins can capture a piece of the invading viral DNA. They then carefully cut and paste this new viral mugshot into the CRISPR archive, adding it as a new spacer in the sequence. This archive then serves as a memory bank. The cell makes small RNA copies of these spacers, which act as guide molecules. These guide RNAs attach to a protein, the most famous of which is called Cas9, which acts as a kind of molecular scissors. The guide RNA then patrols the cell's interior, and if it ever again encounters a virus whose DNA matches the sequence in its memory, it locks on, directing the Cas9 protein to cut the invading DNA, destroying the virus before it can cause any harm. The discovery of this beautiful, natural mechanism was a monumental piece of science in itself. But the final, world-changing serendipity was the realization, by scientists like Jennifer Doudna and Emmanuel Charpentier, that this ancient bacterial defense system could be harnessed, that it could be repurposed. They realized that if you could create your own artificial guide RNA, you could, in principle, load it into the Cas9 protein and send those molecular scissors to cut any DNA sequence you wanted, in any organism. A tool that bacteria had evolved over billions of years to defend themselves had, in a flash of human insight, become the most powerful and precise gene-editing technology ever discovered. We did not invent this technology. We found it by patiently noticing a strange pattern and slowly, over many years, learning to understand its profound purpose. It is a humbling and wondrous reminder that the deepest wisdom and the most powerful tools are often not the ones we build from scratch, but are the ones we discover, waiting silently in the ancient, living archives of life itself. From the discovery of a profound biological secret hidden in the archives of life on Earth, our journey now lifts its gaze one last time to the heavens, to a story that beautifully reverses this flow of discovery, the tale of a fundamental element of our own world that was found not in a mine or a laboratory, but in the ethereal, golden light of the sun. Our story begins on August 18th, 1868, as the shadow of the moon sweeps across the Indian subcontinent. A total solar eclipse is a rare and breathtaking spectacle, a moment when the clockwork of the cosmos reveals its majesty, and astronomers from across the globe have gathered to witness it. Among them is a French astronomer, Pierre-Jules César Janssen. He has travelled to the city of Guntur, armed with a revolutionary new instrument called a spectroscope. This device is a kind of prism that takes a beam of light and splits it into its constituent colours. Its spectrum, a rainbow barcode that reveals the chemical fingerprints of the elements that produce the light. During the few precious twilight minutes of totality, as the brilliant face of the sun is hidden, the fiery atmosphere of the sun, the chromosphere, becomes visible. Janssen points his spectroscope at the great, arcing plumes of gas, the solar prominences, that erupt from the sun's edge. He sees the bright, familiar spectral lines that signify the presence of hydrogen. But then, he sees something else. A brilliant, vivid yellow line that he has never seen before. A line that does not correspond to the fingerprint of sodium or any other element known to exist on Earth. In that fleeting moment, Janssen had a flash of insight. The spectral lines from the prominences were so bright, he realized, that he might be able to see them even without an eclipse, if he could find a way to isolate that specific wavelength of light. He worked tirelessly, and the very next day he succeeded, becoming the first person to observe the solar atmosphere in broad daylight. At the very same time, halfway around the world in England, another astronomer named Norman Lockyer was independently developing a similar technique. A few weeks after Janssen, he too pointed his spectroscope at the edge of the sun and saw the same mysterious yellow line. Both men, Janssen and Lockyer, had made the same discovery almost simultaneously. They were convinced that this was the signature of a new element, an element that, as far as anyone knew, existed only in the sun. Lockyer and his colleague, the chemist Edward Frankland, proposed a name for this new solar substance. They took the ancient Greek word for the sun, helios, and from it they named the element helium. For the next 27 years, helium was a celestial phantom, an element that existed only as a strange yellow line in the light from a distant star. It was a discovery of breathtaking audacity, a moment when humanity reached out across 93 million miles of empty space with nothing but a prism and the power of reason and plucked a new element from the heart of the sun. The story, however, was not yet complete. The second half of this cosmic serendipity would unfold back on Earth, in a London laboratory in 1895. The Scottish chemist William Ramsay was investigating a piece of uranium-bearing rock called clevite. He was searching for argon, a noble gas he had recently co-discovered. When he treated the rock with acid, it fizzed and released a gas. Believing it might be argon, he collected a sample, and using his own spectroscope, he passed an electric current through it to make it glow. He looked at its spectrum, and he was met with a dazzling, unexpected sight. A brilliant, piercing yellow line, a line that had haunted the notebooks of astronomers for nearly 3 decades. It was a perfect, unmistakable match. The element born in the sun was also here on Earth, a terrestrial prisoner, locked away inside a humble, radioactive stone. The two discoveries, separated by an ocean and a generation, finally clicked together to tell a much grander story, the story of our own cosmic origins. The science that unites these two moments is the science of stellar nucleosynthesis. Our universe was born in the Big Bang with almost nothing but the lightest elements, hydrogen and a small amount of helium. The heavier elements that make up our world, the carbon in our bodies, the oxygen we breathe, the iron in our blood, were all forged in the unimaginable heat and pressure at the core of stars. In this stellar furnace, hydrogen atoms are fused together to create helium. This is the first and most fundamental step in the creation of the elements. The helium that Janssen and Lockyer saw in the sun was the product of this ongoing fusion. The helium that Ramsay found trapped in a rock was mostly the product of a different process. The slow, steady, radioactive decay of heavy elements like uranium, elements which themselves could only have been created in the cataclysmic, explosive death of a giant, ancient star. And so, the story of helium, found first in a star and then under our feet, is the ultimate confirmation of our connection to the cosmos. It whispers a profound and beautiful truth, that the Earth and everything on it is made, quite literally, from the ash of long-dead stars. It is a discovery born of two perfect accidents that, together, remind us that we are children of the sun, woven from the fabric of the cosmos. Having journeyed to the heart of a star to find the origins of the elements that make us, our path now turns inward, into the most mysterious and intimate cosmos of all, the universe of the human mind, where we find that a substance with no power at all can, through the strange alchemy of belief, create profound and measurable change. We begin our final, contemplative act with a phenomenon that is not new, but has been hiding in plain sight for all of human history. For as long as there have been healers and patients, there have been placebos. Inert substances, like bread pills or coloured water, prescribed with conviction and taken with faith. The effect they produced, the very real relief they could sometimes provide, was long known, but it was dismissed by the emerging rigour of modern science. It was seen as mere imagination, a trick of the mind, or worse, a form of foolishness or deception. In the world of scientific medicine, the placebo effect was a ghost in the machine, a nuisance to be eliminated from experiments, a shadow of error that obscured the light of real, pharmacological truth. The serendipitous discovery of the placebo effect was not, therefore, the discovery of a new thing, but the slow, dawning realization that the shadow itself was a thing of profound importance. This realization came into sharp focus through the harrowing experiences of an American anesthesiologist named Henry K. Beecher during the Second World War. The scene is a chaotic field hospital on the Anzio beachhead in Italy in 1944, a place of immense suffering and dwindling supplies. Beecher is working tirelessly to treat grievously wounded soldiers, but the hospital is running dangerously low on its most crucial resource: morphine. One day, another horribly injured soldier is brought in excruciating pain, his body on the verge of going into circulatory shock. Beecher knows the soldier needs morphine immediately, but he has none left. A quick-thinking nurse, unwilling to let the soldier suffer, fills a syringe with a simple, harmless saline solution. She approaches the soldier with confidence and care, telling him that this is a powerful new painkiller that will bring him relief. Beecher watches, expecting nothing. But to his utter astonishment, the soldier's breathing calms. The look of agony on his face softens. His pain visibly subsides, and his vital signs stabilize. The simple salt water, administered with a story and a touch of hope, had worked just as well as a potent opioid. Beecher witnessed this same small miracle again and again during the war. In the crucible of combat, he came to a profound realization. The mind of the patient was not a passive bystander in the process of healing. The belief, the expectation, the meaning of the treatment was a powerful medicine in itself. The ghost in the machine was real. This was serendipity, born of desperation. The placebo effect had always been there, a quiet murmur in the background of medicine. But it took the extreme circumstances of a war zone, a place stripped of all but the most essential truths, for a prepared mind like Beecher's to finally hear the murmur as a clear and powerful signal. After the war, he became a tireless advocate for a new kind of scientific rigor. In a landmark 1955 paper titled The Powerful Placebo, he argued that any new treatment must be tested not just on its own, but against an inert placebo. This led to the establishment of the gold standard of clinical research, the double-blind, placebo-controlled trial. In a beautiful irony, the very scientific method designed to control for and eliminate the placebo effect became the precise tool that allowed us to finally measure it, to study it, and to prove its existence beyond any doubt. This work helped to launch the modern field of psychoneuroimmunology, the scientific study of how our thoughts, emotions, and beliefs directly influence our nervous system, our hormone levels, and even the behavior of our immune cells. We now know that the act of receiving a placebo can trigger the brain to release its own natural pain-killing chemicals, the endorphins. It can reduce the production of stress hormones, and it can measurably alter the course of an illness. The placebo is not just in the mind. It is the mind acting upon the body, a real and tangible biological process. And so, as we settle into a state of deep rest, we can reflect on this gentle and powerful truth. The discovery of the placebo effect is the story of science, learning to respect the profound mystery of our own inner world. It is a quiet affirmation that within our own consciousness there lies a deep and mysterious pharmacy, a source of comfort and healing that is unlocked not by a chemical, but by the gentle power of hope. The discovery that the mind itself can be a powerful medicine leads us to a deeper question, to the very heart of our journey tonight. What is it that allows a discovery to be made at all? We return to that beautiful phrase from Louis Pasteur, that chance favours only the prepared mind, and we will now wander through that gentle idea, exploring the rich soil in which the seeds of serendipity take root. A prepared mind is not necessarily the most brilliant mind, nor the one most filled with facts and figures. It is something quieter, something softer. It is, perhaps most importantly, a mind that is receptive. It is a mind that has cultivated the gentle art of noticing. Think of Alexander Fleming pausing before a contaminated dish, or Wilhelm Röntgen glancing at a shimmering screen across his darkened lab. These were not moments of active, directed searching. They were moments of passive, open-eyed observation. The prepared mind is like a beachcomber who wanders along the shore not with a specific treasure map, but with a deep and abiding curiosity for whatever the tide might bring in. while others walk past, lost in thought. The beachcomber pauses to examine a strangely shaped shell, a peculiar piece of driftwood, a glint of coloured glass. It is this habit of pausing, of looking closer at the things that do not fit the pattern, that defines the very essence of a mind that is ready for discovery. This readiness also requires a profound openness, a willingness to let go of what we think we know. A mind that is too rigid, too attached to its own theories, will often explain away an anomaly rather than explore it. When Vera Rubin's data showed that galaxies were spinning too fast, the established theories of gravity told her this was impossible. A less prepared mind might have distrusted the data, assuming an error in the equipment or the calculations. But her mind was open enough to trust the evidence of her own careful observations, a choice that led to the discovery of dark matter. When Henri Becquerel saw his photographic plate, deeply fogged in the darkness of a drawer, he had to abandon his own cherished hypothesis about sunlight and phosphorescence. This is an act of quiet courage. It is the ability to stand before a mystery and admit, "I do not know," which is the first, essential step towards truly knowing anything at all. The prepared mind is not afraid of being wrong. It is excited by the possibility of finding a new, more interesting truth. Sometimes, a mind becomes prepared only through the slow, gentle passage of time and a change in perspective. Consider the strange and sticky story of superglue. In 1942, a scientist named Harry Coover was working to create clear plastic for precision gun sights for the war effort. In his experiments, he synthesized a class of chemicals called cyanoacrylates. The substance was a complete and utter failure for his purposes. It was not stable, and worse, it had the infuriating property of instantly and permanently bonding to every single piece of equipment it touched. He and his team dismissed it as a useless, frustrating nuisance and moved on. 9 years later, Coover was working at a different company, on a completely different project, developing heat-resistant canopies for jet fighters. A member of his research team was testing a new formulation of these same cyanoacrylates, and in a moment of frustration, he ruined an expensive piece of optical equipment by gluing the lenses together. But this time, instead of just annoyance, a spark of insight ignited. Coover realized that they had been looking at the substance all wrong. They were not looking for an adhesive, but in that moment, they saw that the problem of its stickiness was, in fact, its single greatest strength. The mind of Harry Coover had, over 9 years, and in a new context, become prepared to see the solution that had been right in front of him all along. And so, the prepared mind is not just a mind that is curious and open. It is a mind that has a rich and varied landscape of knowledge, a wealth of different ideas and experiences that it can draw upon. It is a mind that has collected many different dots, so that when a new, unexpected dot of information appears, it has a greater chance of forming a new and meaningful connection. In the end, we can think of the prepared mind not as a fortress, filled with defenses and certainties, but as a garden. The gardener cannot command the seeds of chance to fall from the sky. They cannot predict when or where they will land. But the gardener can tend the soil, can keep it soft and moist and free of weeds, can create a welcoming and nourishing environment. And so, when a seed of serendipity does, by chance, drift down from the heavens, it finds a place that is ready to receive it, a place where it can germinate, take root, and bloom into something beautiful and new. To cultivate a mind that is open and prepared like a garden is a beautiful ideal, but the seeds of serendipity, when they bloom, can sometimes produce a strange and challenging flower, a discovery that forces us to confront the uncomfortable truth that our most cherished stories about the world may be wrong. The journey of discovery is not always a joyful one. It can be unsettling, disorienting, and it can demand that we let go of beliefs that have given us comfort and meaning. This human struggle in the face of disruptive new evidence was never more clearly observed than in a fascinating and serendipitous study from the mid-20th century. Our story begins in the early 1950s with a social psychologist named Leon Festinger. He and his colleagues heard of a small, secretive group led by a woman who claimed to be receiving messages from aliens. She had prophesied that on a specific date, a great flood would destroy the world, but that a flying saucer would land at midnight to rescue the true believers. Festinger saw a unique opportunity to study the psychology of belief. He and his team infiltrated the group, pretending to be believers themselves, so they could observe what would happen when the prophecy inevitably failed. On the appointed night, the believers gathered in their leader's home, full of faith and anticipation. Midnight came and went. The clocks ticked on. No saucer appeared in the sky. The world outside remained stubbornly unflooded. A profound and painful silence fell over the room. The group was plunged into despair and confusion. Festinger and his team watched, expecting the believers to finally admit they had been wrong, to see their faith crumble in the face of undeniable reality. But then, something completely unexpected happened. After a few hours of desperate waiting, the leader received a new, divine message. The aliens had decided to spare the entire planet from destruction, precisely because of the unshakable faith of this one small group of people. Their devotion had saved the world. A wave of elation swept through the room. Their belief was not only intact, it was now stronger than ever before. And for the first time, these secretive people, who had previously shunned all publicity, began to call newspapers and go out into the streets to spread their message and seek new converts. This baffling outcome was the true, serendipitous discovery of the study. From these observations, Festinger developed his groundbreaking theory of cognitive dissonance. He proposed that we human beings feel a deep internal discomfort, a dissonance, whenever we are confronted with powerful evidence that contradicts a deeply held belief. To resolve this painful feeling, it is often psychologically easier for us to invent a new and elaborate justification for our belief than it is to simply let the belief go. This profound insight into human nature shines a gentle light on the process of science itself. Scientists, after all, are human. When a serendipitous discovery emerges that shatters a long-held theory, it can create a powerful cognitive dissonance within the entire scientific community. The beautiful, elegant story that has explained the world for generations is suddenly under threat. Think of the Michelson-Morley experiment in 1887. It was designed to prove the existence of the luminiferous ether, the invisible, space-filling substance that was thought to be the medium that carried light waves. The experiment was a masterpiece of precision, but it famously failed. It found no evidence for the ether at all. This accidental null result was a catastrophe for physics. For years, brilliant minds tried to invent complex, ad hoc explanations to save the theory of the ether, to resolve the dissonance. It was psychologically easier to patch up the old, familiar story than to face the terrifying possibility that the story was fundamentally wrong. It took the prepared mind of a young Albert Einstein, who was willing to let go of the old story completely, to propose his theory of special relativity, a new story in which the ether was simply not necessary. Serendipity, then, is often a difficult messenger. It arrives unannounced and tells us that a comfortable story must come to an end. But this process, this graceful, if sometimes painful, dismantling of an old idea to make way for a new one, is the very heart of scientific progress. And it is a gentle model for our own lives. There is a deep and quiet comfort to be found in embracing the truth, even when it means we must say a fond and respectful farewell to a beautiful story we once held so dear. While the journey of letting go of an old story can be a difficult one, the reward is always a new story that is grander, more beautiful, and more deeply interconnected. As we near the end of our journey tonight, we will gather these scattered threads of accidental wonder, from the quantum realm to the forest floor, and see how they weave a single, unbroken tapestry of a universe that is both stranger and more unified than we could have ever imagined. Our story takes us first to the smallest possible scale, to the strange and bewildering world of quantum mechanics. In the early 20th century, physicists conducting the famous double-slit experiment found themselves faced with a reality that seemed to defy all logic. When they fired single particles, like electrons, at a screen with two slits, the particles behaved like waves, passing through both slits at once and creating an interference pattern on the other side. But the moment they tried to set up a detector to see which slit the particle actually went through, the serendipitous and mind-bending discovery was that the very act of looking, the simple act of observation, forced the electron to abandon its wave-like behavior and act like a simple, solid particle, passing through only one slit. This was not a flaw in the experiment. It was a fundamental feature of reality. Scientists, in their attempt to be objective observers, had accidentally discovered that there is no such thing as a truly objective observer at the quantum level. The observer and the observed are an inseparable, unified system. This is perhaps the most profound serendipity of all. In trying to map the world, we discovered that we are, in a very real way, helping to draw the map. We are not just spectators of the cosmic dance. We are participants. From this impossibly small scale, let us now leap to the vast, living systems of our own planet. For a long time, ecologists viewed an ecosystem as a collection of individual species. But a series of accidental discoveries revealed a much deeper truth. In one of the most famous examples, conservationists reintroduced a small number of wolves into Yellowstone National Park in 1995, after a 70-year absence. The intended goal was simply to manage the park's large elk population. But what happened next was a cascade of unforeseen and miraculous consequences. The presence of the wolves did not just reduce the number of elk. It changed their behavior. The elk began to avoid the open valleys and riverbanks where they were vulnerable. In these areas, with the pressure of grazing suddenly gone, the long-suppressed willow and aspen trees began to flourish. This brought back the beavers, who used the new wood to build their dams. These dams created new pond and marsh habitats for otters, muskrats, and fish. The recovering trees also attracted songbirds, and their shade cooled the rivers, benefiting the trout. The wolves even changed the physical geography of the park. The revitalized root systems of the trees stabilized the riverbanks, reducing erosion, which made the rivers meander less and form deeper pools. The accidental discovery was not that wolves hunt elk, but that the presence of a single keystone species could echo through every level of an ecosystem, from the trees, to the birds, to the beavers, and even to the very shape of the land itself. What connects the strange dance of a subatomic particle to the intricate web of a national park? It is the beautiful and profound concept of emergence. The idea that complex, orderly, and unpredictable systems can arise from the interaction of many simple, individual parts. The universe, it seems, is built upon this principle. The intricate, six-fold symmetry of a snowflake emerges from the simple rules of how water molecules bond. The breathtaking, coordinated flight of a flock of starlings emerges from each individual bird following a few simple rules in relation to its neighbors. Consciousness itself may be an emergent property of the trillions of simple connections between neurons in our brain. Each story of serendipity we have explored tonight is a moment when we have accidentally stumbled upon one of these hidden, emergent connections. Fleming's mold and the bacteria were part of an ancient, ecological conversation. Kekule's dream revealed the elegant, stable ring that emerges from the simple bonding rules of carbon atoms. The reintroduction of the wolves to Yellowstone revealed the emergent property of a healthy, resilient ecosystem. All of these discoveries, from the quantum to the cosmic, from the chemical to the biological, are not separate stories. They are chapters in the same grand narrative, a narrative of a universe that is profoundly and reassuringly interconnected, a universe that is constantly weaving itself into new and more complex patterns of beauty, a single, unbroken thread of accidental wonder. To feel our place within this vast, interconnected, and emergent universe is the ultimate gift of science. And as our long story comes to its gentle close, we find ourselves returning to the simple, quiet place where our journey began. Not in a grand theory, but in the humble and gentle art of noticing. Our journey tonight has been a long and winding one. We began with the silence of a forgotten dish of mold, and from there we felt the surprising warmth of a melted candy bar and the gentle, apologetic adhesion of a failed glue. We tasted an unexpected sweetness on a chemist's unwashed hands, and we saw a brilliant, regal purple bloom from a beaker of black sludge. We followed the uncharted currents of medicines as they found new and surprising purposes within the body. And then our gaze turned outward. We peered through the veil of our own flesh with a new and invisible light. We felt the silent, steady glow of a forgotten stone, and we heard the precise, rhythmic heartbeat of a distant, spinning star. We listened, in a quiet field in New Jersey, to the faint persistent static from the very dawn of time, and we saw the ghostly, gravitational grasp of unseen matter holding the great galaxies together in a silent embrace. We returned to Earth and learned to forge new kinds of matter in a flask, creating malleable chains that would rebuild our world. We took a dizzying bicycle ride through the mind's eye, and in the quiet of a dream by a fire, we saw a serpent swallow its own tail and reveal a secret of creation. We found an ancient library of life's defense hidden in the genetic code of bacteria, and we discovered an element of our world by first seeing it in the light of the sun. We felt the profound healing power of pure belief, and we learned the quiet comfort that can be found in letting go of a beautiful story to make way for a truer one. And finally, we saw how all these threads, from the smallest particle to the grandest ecosystem, are woven together into a single, unbroken tapestry of accidental wonder. The one thread that runs through every single one of these tales, the unifying force behind every discovery, is a simple, quiet, human moment. It is the moment when someone, in the midst of their ordinary work, paused. A moment when they tilted their head and looked closer at something that did not fit. It is the gentle art of noticing, and it is the most powerful tool in the universe. Our journey has shown us that the world is not a finished book to be read, but a living, breathing poem that is still being written. The fact that serendipity plays such a profound role in our understanding is not a sign of our incompetence. It is a testament to the universe's infinite capacity for surprise, and there is a deep and abiding peace to be found in this. It means that there will always be more wonder than we can imagine. There will always be new secrets waiting in the quiet corners, new melodies to be overheard, new patterns to be glimpsed. It means that the world will never be a boring or predictable place. And this gentle art of noticing is not reserved for scientists in their laboratories. It is a capacity that lives within all of us. We may not discover a new form of energy or a new law of nature, but we can cultivate the same prepared and gentle mind in our own lives. We can practice noticing the small, unexpected moments of grace that drift into our own days. The surprising kindness of a stranger, the unexpected way the afternoon light falls across a familiar room, the synchronous arrival of a forgotten memory just when we need it most. These are the serendipities of the soul, the happy accidents of a life lived with open eyes. So as you now let go of the day, as your body grows heavy and your mind begins to drift, carry this one gentle thought with you into your sleep. Carry with you a sense of quiet wonder. May your mind be like a well-tended garden, open and receptive to whatever seeds of chance may fall. And may your dreams be filled with the same sense of beautiful, unpredictable, and gentle magic that fills our waking universe. Thank you for joining me on this long journey through the world of scientific wonder. I hope these stories have brought you a measure of peace and comfort. I would love to read your own thoughts or reflections in the comments below. If you have enjoyed our time together, please consider showing your support with a like and by subscribing to the channel for more gentle stories for sleep. Wishing you a deep and truly restorative rest. Good night.